A charge pump is a kind of DC to DC converter that uses capacitors as energy storage elements to create either a higher or lower voltage power source. Charge pump circuits are capable of high efficiencies, sometimes as high as 90–95%, while being electrically simple circuits. Charge pumps use some form of switching device, to control the connection of voltages to the capacitor. For instance, a two-stage cycle can be used to generate a higher pulsed voltage from a lower voltage supply. In the first stage of the cycle, a capacitor is connected across the supply, charging it to that same voltage. In the second stage of the cycle, the circuit is reconfigured so that the capacitor is in series with the supply to the load. Ignoring leakage effects, this effectively provides double the supply voltage to the load. The pulsing nature of the higher voltage output is typically smoothed by the use of an output capacitor. An external or secondary circuit drives the switching, typically at tens of kilohertz up to several megahertz. The high frequency minimizes the amount of capacitance required as less charge needs to be stored and dumped in a shorter cycle. The capacitor used as the charge pump is typically known as the flying capacitor. Another way to explain the operation of a charge pump is to consider it as the combination of a DC to AC converter followed by a voltage multiplier. The voltage is load-dependent and higher loads result in lower average voltages. Charge pumps can double voltages, triple voltages, half voltages, invert voltages, fractionally multiply or scale voltages and generate arbitrary voltages by quickly alternating between modes, depending on the controller and circuit topology. Terminology for PLL: the term charge pump is also commonly used in phase-locked loop circuits even though there is no pumping action involved, unlike in the circuit discussed above. A PLL charge pump is merely a bipolar switched current source. This means that it can output positive and negative current pulses into the loop filter of the PLL. It cannot produce higher or lower voltages than its power and ground supply levels. Applications: a common application for charge pump circuits is in RS-232 level shifters, where they are used to derive positive and negative voltages from a single 5V or 3V power supply rail. Charge pumps can also be used as LCD or white LED drivers, generating high bias voltages from a single low-voltage supply, such as a battery. Charge pumps are extensively used in NMOS memories and microprocessors, to generate a negative voltage VBB, which is connected to the substrate. This guarantees that all N+2 substrate junctions are reverse biased by 3V or more, decreasing junction capacitance and increasing circuit speed. A charge pump providing a negative voltage spike has been used in NES-compatible games not licensed by Nintendo in order to stun the Nintendo Entertainment System lockout chip. As of 2007, charge pumps are integrated into nearly all EEPROM and flash memory integrated circuits. These devices require a high voltage pulse to clean out any existing data in a particular memory cell before it can be written with a new value. Early EEPROM and flash memory devices required two power supplies, plus 5V and plus 12V. As of 2007, commercially available flash memory and EEPROM memory requires only one external power supply, generally 1.8V or 3.3V. A higher voltage, used to array cells, is generated internally by an on-chip charge pump. Charge pumps are used in H-bridges in high-side drivers for gate driving high-side N-channel power MOSFETs and IGBTs. When the center of a half-bridge goes low, the capacitor is charged via a diode, and this charge is used to later drive the gate of the high-side FET gate a few volts above the source voltage so as to switch it on. This strategy works well provided the bridge is regularly switched and avoids the complexity of having to run a separate power supply and permits the more efficient N-channel devices to be used for both switches. This circuit may also be called a bootstrap circuit, and some would differentiate between that and a charge pump. References: Gen. F. Substrate bias circuit, U.S. Patent 3794862A, February 26, 1974. Kevin Horton. Claude Dreams Revision C. Last modified September 30, 2007. Access September 15, 2011. applying the equivalent resistor concept to calculating the power losses in the charge pumps. J. C. Maxwell, A Treatise on Electricity and Magnetism, Oxford, The Clarendon Press, 1873, pages 420 425, OE intermittent current, Art 775, 776. Z. Singer, A. Emanuel, and M. S. Ilicki, OE power regulation by means of a switched capacitor, in Proc. Of the Institution of Electrical Engineers, Volume 119, A-2, 1972, pages 149 152. G. Van Steenwedge, K. Hon, and H. Wallinger, OE analysis and design of a charge pump circuit for high output current applications, in Proc. 19th European Solid-State Circuits Conference 1993, pages 118 121. J. W. Kimball, P. T. Crin, and K. R. Cahill, OE modeling of capacitor impedance in switching converters, IEEE Power Electronics Letters, Volume 3, A-4, 2005, pages 136 140. K. Ito, M. Horiguchi, and H. Tanaka, Ultra-Low Voltage Nanoscale Memories, Series on Integrated Circuits and Systems, Springer, 2007, 400p. M. D. Seaman and S. R. Sanders, OE analysis and optimization of switched capacitor DC-DC converters, IEEE Transactions on Power Electronics, Volume 23, A-2, 2008, pages 841 851. S. Benyakov and M. Evselman, OE generic and unified model of switched capacitor converters, IEEE Energy Conversion Congress and Expo 2009, pages 3501 3508. S. Benyakov, On the Influence of Switch Resistances on Switched Capacitor Converters Losses, IEEE Transactions on Industrial Electronics, 2011. Charge pumps where the voltages across the capacitors follow the binary number system, F-Wano, T-Anu, and IRTA, OE realization of a new switched capacitor transformer with a step-up transformer ratio 2:1 using N capacitors, IEEE International Symposium on Circuits and Systems 1986, pages 805 808. J. A. Starzik, Y.W. Jan, and F.Q., OE DC-DC charge pump design based on voltage doublers, IEEE Transactions on Circuits and Systems, Part 1, Volume 48, A-3, 2001, pages 350 359. F. L. Leo, and H. E., OE positive output multiple lift push pull switched capacitor Leo converters, IEEE Transactions on Industrial Electronics, Volume 51, A-3, 2004, pages 594 602. S. Benyakov and A. Kushnarov, OE algebraic foundation of self-adjusting switched capacitors converters, IEEE Energy Conversion Congress and Expo 2009, pages 1582 1589. External links, charge pump, inductorless, voltage regulators, on-chip high-voltage generator design, charge pump DC-DC converters. Applications, circuits and solutions using inductorless DC-DC converters. DC-DC conversion without inductors. General description of charge pump operation. Example applications using Maxim controllers. Charge pump and step-up DC-DC converter solutions for powering white LEDs in series or parallel connections, circuit board layout guidelines for white LED charge pumps, linearized three-state phase detector by Stephen F. Gillig, linearized digital phase and frequency detector by John D. Hatchett and Andrew S. Olezin, charge pump circuits overview. Tutorial by G. Palumbo and D. Papalado. See also, Cockcroft-Walton generator, voltage multiplier, switched capacitor, charge transfer switch, voltage doubler.